Hey everybody, what's going on? How's it going? So we're back. Welcome back to my channel. Thank you for tuning in. So I started dumping all of my to-dos into a to-do.md file over here, and I want to start showing and sharing my to-do list as I relearn mathematics and stream and share the whole progress. So today, the highlighted line 18. Goal for today on this stream is to continue working through the natural number game. So this is number theory, episode number day 11, essentially. And we are continuing the natural number game, as I said. So what is the natural number game? It is the tutorial to learn Lean. Lean is the most modern version and flavor of proof-based mathematics. So instead of being based in set theory, which has challenges and problems, and it has its critics, there is a group of mathematicians out there attempting to reformulate all of mathematics grounded in type theory, which is a little bit more concrete. And you can even feed it to a computer, and you can get a computer to validate, yes, this is a correct proof, or no, this is not a correct proof. So join me. We're going to be playing the natural number game. You can start it yourself. I think anybody could play this game. It is very fun. It is a very cool way to try to learn mathematics, I think, and proof-based mathematics. Hey, Viking Doomslayer, it's good to see you, man. Thanks for joining the chat. Cool, so let's get started. What else? This is my to-do syntax, by the way. I always like to put little priority divider lines, like on line 7. I don't know if I'm going to do it on stream, but I really need to finish this Hetzner deployment of my shiny new thing that I've mentioned that I was working on a few streams ago. We might turn this into a Pomodoro work with me, study with me stream, and I'll just do that privately, or not. I don't know yet what I want to do. One thing I did want to mention, though, here, this was freaking cool. Line 17. This morning I woke up and I saw an email, and I think it's 100% a coincidence. But this morning, a group emailed me saying, seeking mathematicians, seeking experts in Lean. And there's one of many groups out there trying to formulate and pay contractors to translate mathematics into Lean problem statements and solutions. They're looking for people with competitive math experience, which I have. I've done the Putnam exam in university. And they're looking for mathematicians who can translate math into this very modern computer executable syntax and programming language of Lean. So I emailed back and I was just like, dope. I mean, that's what I want to do. I guess since yesterday there's been a couple updates. I really did a lot of research yesterday looking into grad schools, and I think that's what I want to do. I think I want to go to grad school, and I don't know if I want to do a computer science master's degree or a pure math master's degree. But I think in either case, I'm really interested in AI-assisted pure mathematics, AI-assisted mathematical reasoning using Lean. I'm super interested and motivated by this problem space, and I think I've got a lot that I could offer and contribute to in this field. So join me on this journey. We're going to continue, as I said, this tutorial series this week, but at some point I'm going to get back to more classical proofs and classical mathematics, classical proof-based mathematics, and I'll be trying to translate those classical proofs over to Lean proofs, and just doing both and blending both at the same time. So join me. I hope that this is going to be fun. Let me grab... Here's the link if anybody out there wants to follow along and play this game with us, wherever the heck it is. Let's see. Hey, Viking Doomslayer, good to see you, man. Thank you for tuning in. Here is the natural number game if anybody out there wants to play it alongside us. So, all right, this is going to be fun. And let's listen to some classical guitar in the meantime. your classic, iconic pretzel. Good to see you, dude. How are you? Shouldn't you be in school or something? Okay, so let's get to it. Alright, so here's the natural number game. I can try to quickly recap what we've done yesterday. Yesterday we went through tutorial world, addition world, and multiplication world. I solved all of those first levels, I guess you could call them. Here, does this one? This is optimized for this purpose. Okay. And in the first video yesterday, I lost my audio halfway through. But, oh well, you know, these things happen, right? So, and then in the second video, I just solved more problems more privately on my own. So I'll just read through these really quickly for those who haven't seen this yet. Welcome to Tutorial World. The goal is to prove really simple mathematics, like 2 + 2 = 4. How do we put that on very firm foundations? Like, what is the simplest assumptions that we can take as axioms and postulates in order to make that a theorem and a proof? Like, this is a result of simpler things. Like, you learned this in elementary school, but for advanced mathematics, this is actually something that you prove to be true. So in Lean, you prove theorems by solving puzzles using tools called tactics. And then in Tutorial World, we learn some basic tactics. RFL is the tactic that you use when the left-hand side equals the right-hand side. Then if you have a goal like this, 2y = 2 times x + 7, and you assume that y equals x + 7, all we need to do is substitute y. We want to substitute in, so we rewrite y as x + 7 in the left-hand side. So this command, rw, is the rewrite command. So by rewriting, in other words, substituting for y, now the left-hand side equals the right-hand side, and we can use reflexivity. Then, in part 3, what is our goal? Our goal is that 2 equals the successor of the successor of 0. So in piano arithmetic, you only have one number. You have the number 0, and then you say that the symbol 1, well, you have one number, the number 0, and then another axiom is anytime you have a number, including 0, you also have another number called the successor of 0, of your number n. So, the definition, it says that we use, when we write down the symbol 1, what we really mean is successor of 0. And by the symbol 2, we mean the successor of the successor of 0. In other words, if you have a number, you have a following number. You can count and you can get another number after it. So we have this inventory system where we have a set of definitions of addition. We have add 0, we have add successor. Those are both definitions. And somewhere in here in piano arithmetic, or 0, 1, 2, these are the definitions of 1 is defined as the successor of 0. And then in this theorem or goal that we have, we want to show that 2 is the successor of 0. So we can rewrite 2 as a successor of 1, and then we rewrite 1 as a successor of 0, and now the left-hand side equals the right-hand side. So we use reflexivity. Now we have rewriting backwards. This is still just a tiny bit confusing to me, but I think I understand. It's just kind of hard to describe why. So 1 equals successor 0. You would use rewrite 1 equals successor 0 to replace successor 0 with 1, I think. Or no. To replace the symbol 1 with successor 0. But we don't have the symbol 1 in this statement. We only have successor 0. So by using this arrow, we go the other way. We say successor 0 equals 1. And we substituted a 1 instead of successor 0. Then we can rewrite successor of 1 is 2. And now we have left-hand side equals right-hand side. So we have reflexivity, and so we're done. Here in this world, we add 0. We make the definition that adding 0 to any number does nothing. So in this section, we're starting to define what does addition mean. And we define it as either you add 0 or you add the successor of a number. And then, so we define adding 0 to do nothing. It just returns the number x. So here, I use the tactic add 0 of b, and then that replaced b plus 0 as b. And then I rewrote another add 0, and that's going to replace c plus 0 with just c right here. Now the left-hand side equals the right-hand side, so we can continue. Precision rewriting points out that we can either include this parameter or not. So if I do rewrite add 0c, it is going to target this specific case of adding 0. Whereas if you don't include that parameter, it will just apply to the first place in the statement, in the goal, where it can rewrite that term. So instead, so we replace that, then we replace b plus 0 with b, and now left-hand side equals right-hand side. Add successor in this. 1 equals the successor of 0, so we replace that 1 with successor 0 here. And now we define successor, like a number plus a successor of a number is the same as the successor of the two numbers added together. So in a sense, you can like kind of pull that successor function out. It's kind of like saying n plus 1 equals 1 plus n in this case. Or x plus y plus 1 equals 1 plus x plus y. Like you can always, if you're adding 1 in the middle of a statement, you can add 1 first and then add everything else. It's kind of like that. So we pull this plus 1 out to the left here, and now we have n plus 0, and well, n plus 0 is, we can substitute that as just n, because we have this theorem or definition that we created before. Now the left-hand side equals the right-hand side, so we can continue. Now we can rewrite terms, and we can even specify which application we want. So in the second place where we have the number 2, we're going to replace it with successor 1. And then now I am going to pull out the successor function here. Now successor of 2 plus 1, we rewrite 1 as a successor of 0, and then we pull out the successor again to the left. So now we have successor of 2 plus 0. Now 2 plus 0 is just 2. So now we have a nice statement on the left. Next I'm going to work on the right, and I'm going to say that 4 is successor of 3. I'm going to say that 3 is a successor of 2. And now we have left-hand side equals right-hand side. And then you're done with tutorial world. So that was fun. I'm just reviewing what we did yesterday. I will just quickly say what the other worlds are about without going through all of the details. In addition world, we introduce induction. You can go back to one of my prior videos, I think number theory 2. I start introducing what induction is. But basically, if you want to prove a statement is true for all numbers, you can show that it works for one number, and then you can show that anytime it's true for one number, it's true for the next number also. So therefore, if you show it's true for 0, then it's also true for 1, and it's also true for 2, and 3, and 4, on and on forever. I think of it like dominoes. You prove that all of the dominoes are close together, and you prove that you can knock over the first domino. And so in this world, we define addition. And we define what that symbol means by induction. And we prove some statements about addition, like 0 plus n equals n. This is in the opposite order. What we had before was n plus 0. Now we're proving that that the reverse is true. 0 plus a number is that number. Then we prove that that you can add the successor on the left of this term, and that it also equals successor of a plus b. We do this again by induction. Then we prove the commutativity of addition, that a plus b equals b plus a, that addition is always commutative. So that's really cool. Then we prove associativity of addition. A plus b parentheses plus c equals a plus parentheses b plus c. So that's dope. We're proving all of these things that we learned in elementary school as just a given, but you don't know why it's true, quote unquote. It's just, you just get used to it when you're young. And here we're proving that it's always true. So now here's associativity on the right, or commutativity for 3 numbers, that we can swap b and c in this associative 3 numbers. And then that's the last statement that we prove in addition. In multiplication world, we define multiplication. We define multiplying by 0 to equal 0. And then we define multiplication by 1. Actually, this is a theorem. So we prove that multiplication by 1 equals the number. We don't need that as a definition. We can use it as a theorem. 0 multiplication, 0 times any number equals 0. Successor multiplication, so this is like a plus 1 times b equals a times b plus b. It's like distributivity on the right, where the second term is 1, like a plus 1 times b. You can think of it that way from school, because n plus 1 is the successor of n for anything. Now, in section 4, you prove commutativity of multiplication. X times y equals y times x, which is pretty dope. Then we have multiplication by 1. For any natural number m, we have 1 times m equals itself. Then we have multiplication by 2, and you prove that 2 times a number is that number added to itself. Then you prove that multiplication is distributive on the left. A times b plus c equals ab plus ac. Then you do distributivity on the right. That if you first add two numbers and then you multiply, that C can distribute as AC plus BC. So again, these are theorems. These are things that we prove. We don't just take it for granted. We actually prove that this is always true. Now we have associativity of multiplication that you prove, which is pretty dope. And then you're done with multiplication world. So that's everything we did yesterday. Today we're going to learn about implications. So we've proved that 2 plus 2 equals 4. In implication world, we'll learn how to prove that 2 plus 2 is not equal to 5. So now, just like how in our previous videos, I don't know where the book is, but I've been working through 2 books for number theory and intro to proofs. I've been using Velleman's intro to proofs book called How to Prove It. So we introduced on stream the idea of propositions. These are like mathematical statements that can either be true or false. So it's false that 2 plus 2 equals 5. That has a truth value to it, and it is false. It is true that 2 plus 2 equals 4. So far in the natural number game, we've only worked with true theorems and statements. Now we're going to introduce implications. And what we're going to say is like, if x is 2 and y is 2, then x plus y does not equal 5. Some like kind of mathematical if-then statements like that. Cool. I think that this is a good moment to pause and ask if there are any questions in the chat. How's it going? I know that was a rapid fire run through of all this. Viking Doomslayer. Oh, I'm sorry that you're sick. Wowie, math is cool. Math is dope, man. Math is beautiful. Why do we have to do so many steps for 2 plus 2? This is too many steps. It's fun, man. Try it yourself. Like, no joke, it is just fun. It's like a video game. And it's because math is a very rigorous language. Math is very grounded in very firm truths. There's a logical system that's beautiful, and yes, like it does feel like a lot of steps, but it is grounded in logic. It's grounded in logic and reasoning as opposed to empirical heuristic arguments. You can't just say, well, every time I've had two objects, if I count them, then there's 4. Like, what does it mean to count them? What does it mean to see 2 things? Like, what does thing mean? Like, we want mathematics to be grounded in super basic, simple truths that we can all agree on. Because by putting it in that kind of a vacuum of really concrete definitions, theorems, logic, then you're able to build from there and build really clear systems that don't have contradictions with itself. So in the past, hundreds of years ago, we used to always do mathematics just like, I don't know, here's a circle, here's another circle. Like, of course they're going to intersect if they're close together. Like, I think the first page of Euclid, there is a kind of hand-wavy argument where he doesn't show all of the intermediate steps. But at the time, it was considered a very rigorous and very formal proof. So mathematics has always tried to have rigorous formal proofs, and Euclid was like the example of rigorous mathematics. But later on, now we realize that you can be even more rigorous and even more clear and more precise in your language. And so in a real sense, all of this stuff that's happening with the lean and reformulation into type theory is like another one of those reformulations and like regrounding math into even simpler truths. That said, all the steps that we've done so far is not really new. This is just translating it into computer programs. And the fact that a computer program can execute it and say, yes, this is a accurate proof, is so useful. But every single step we've done is like, what, 200 years old or so? 150? I don't know exactly when the piano arithmetic axioms came out, like 150 years ago, something like that. So it's relatively new. Like 150 is not that old, but this isn't brand new. All of these steps that we did, every single step, is how math has been, how rigorous and formal math has been for a while. And what's new is that we can run a computer program that checks our steps along the way. So, cool. There's the end of the chaconne. Here's a nice point to get started with the next part. All right, let's do Implication World. Thanks everybody for hanging out. I hope you enjoy this. I'm glad that one viewer enjoyed that little spiel. Where's my phone? Here it is. Let's do some Pomodoros and let's get some work done, y'all. Hey Siri, set a timer for 30 minutes. But yeah, I mean, I think it's so great that they use video game terminology in the natural number game, because it does feel like a video game. It does feel like battling bosses and getting through levels. Like, programming feels like a video game a lot of the time, especially when systems are brand new and fun and easy to reason about. So, yeah, let's play some video games. Alright, so now I'm going to shut up and just focus and get some work done. Hope you all enjoy. Thanks for swinging by.
That's pretty smooth, man. That was pretty smooth. I mean, there's little cosmetic things that you don't like, and we're going to handle. But overall, that's a big improvement from last week. There's two spots where you're compressing the rhythm.
All right, y'all, we are back. We're taking a 5-minute Pomodoro break. Cool, we made some progress here. Hey Siri, set a timer for 5 minutes. So I feel like I'm making a lot of progress. So we're on part 9 of 11 in Implication world. And so what we've been doing is we have been learning how to prove statements like if A, then B. And we're learning how to do propositions and implications in Lean. This is pretty cool. I'm having a lot of fun over here. I know that not everybody is following along, but I promise you, you can catch up. If you want to, you can absolutely catch up to where I am. Pause the video, go catch up, go play Tutorial World, go play the first few worlds of Lean. It's pretty fun, and I've seen this in the past. I ran through this whole tutorial at the beginning of the pandemic in 2020, so this isn't my first time going through it, but I am having to remember like what is the syntax like, and this time around like I'm trying to get like a better understanding exactly of the different types of like why the syntax is built the way that it is, and like I'm taking a look at the inventory more often this time and kind of exploring the documentation a little bit more. So it's pretty cool. So one difference is that right now I just started exploring the editor mode. I think that editor mode is going to be way more like real world coding in Lean. And in particular, I wanted to figure out how can I write down comments, because I wanted to rewrite this last part. Like I know I could have done it in typewriter mode, which is kind of like command line REPL, I think. I think that it's like a read, eval, print loop environment. But in code, I want to be able to write down comments like, okay, at this point, h1 is x equals y, and h2 is x not equal y. And I wanted to rewrite that for myself. What this not equal y means is x equals y implies false. So I wanted to just rewrite that for me as a lowly human who needs to like see that as an implication. And until you get used to it, I think it makes sense to write that out explicitly. And our goal in this was false. And I think that this is going to just be easier for me to read as somebody who is a coder, somebody who's coded before. And now I'm learning how to use the typewriter mode. And it looks like if I click the mouse, maybe it loads the goal state at that line. Is that what's happening here? I don't know. It seems to be getting stuck. Line 7, character 8, unsolved goals. That's not what I expected. I thought that we solved this one completely. Apply H2 at H1. So if we apply H2 at H1, then x equals y implies false. So since this is like a truth, like if x equals y, then we have false. So we can apply this truth to the fact that x equals y in this hypothesis. So then we're going to rewrite H1 as false. And then our goal should be false equals H1, which is now false. Like, I don't know why this is... I think that this is incorrect. Exact H1, apply H2 at H1. Oh, okay, and we can, it looks like we can type in comments into typewriter mode. Look at that. All right, so apply H2 at H1, and that will transform the first hypothesis, into false. And then the state is H1 is now false, and the goal is false. So now we just say exact. The goal is exactly H1. So, execute. I don't know why that's different than what editor mode was. I think that was a bug. Yeah, exact H1. I don't know. I guess I'll... Oh, did I type like exact at H1 or something? It should just be exact H1. Cool. All right, well, break timer is over. Looks like there's no questions or anything of the sort. So why don't we get started with the next Pomodoro? Hey Siri, set a timer for 30 minutes. Hey Siri, set a timer for 30 minutes. All right. And if you haven't realized it, we are listening to my own classical guitar music. So that's fun. Let's see, My Lady Huntston, this has talking in it. Capriccio Arabe has a lot of talking in it. I need to clip out more non-talking music. That's me. That's me. Go subscribe to my other channel, The Guitar Hobbyist. Alright, thanks for watching. Let's get some work done. Let me know, folks, if the audio should be, if the music should be up or down. Cool. Okay, so we're making progress. I mean, the readability contrast is not great against this greenish background because it wasn't built for this dark mode. It was built to be like this, but I don't know. Blinding white on a YouTube video. Is there a dark mode anywhere? There's no dark mode. Yeah, I don't think that there's a dark mode on the site. Okay. And I don't know enough coding to offer to help. I don't know enough about web. I don't do web. I do iOS development, y'all. Okay. Thanks for hanging out. Let's keep going. Cool. We are learning lean. want to learn how to write this. So we want to show that 0 is not equal to 1. Do we have any... So to show 0 is not equal 1, and I don't think we have any hypotheses yet, what we do is we start out by intro at h or intro h. Now h is 0 equals 1, right? And our goal has now been transformed into false because the syntax 0 not equal 1 means 0 equals 1 implies false. So now we just introduce the hypothesis, and then our goal transforms to, if you have this, if this is a hypothesis, then the goal is false. Like assume 0 equals 1. Then we want to show that that is false. So we have this, hypothesis 0 equals 1, goal is false, and now what we can do is we can rewrite 1 equals successor of 0, I think, at h. Okay. Now we've redefined h as 0 equals the successor of 0. What I think we need to do next is rewrite h as can we apply, wait. I was just thinking that we could do something like successor of -1, like 0 equals successor of -1, but we don't have negative numbers. And then goal false. If we could do that, then we could apply that the successor function is injective. And we have a contradiction that the argument of this successor doesn't equal the argument of this successor function. Okay, so I want to see how can we rewrite this in a reasonable syntax that will work for me. So we need to figure out this ... right here. How do we substitute in How do we get false into this? We can read the hint, obviously, but I don't want to read the hint. I want to try to figure this out intuitively so that I can capture that learning a little bit better. Did the timer actually start? I don't think it did. Oh, it did. 0 equals successor 0. What do we have anything? 0 not equals successor. That's what we're proving right now. Successor is injective. Like, we're super close to that, but that's not the right thing. This code looks absolutely horrible here, so I want to clean this up. I guess what I could do is show exactly what each line does by putting them above like this. Like this line transforms the state into this. So intro H will, look at, I kind of want to have the state changes near the lines of code. This isn't going to work. Apply successor is injective at H. This is not going to work. Successor. We're close to what we want. We proved a lot of things about addition, and this is essentially addition, but we haven't proved many things yet. We haven't proved many like propositional statements yet. I think that we do this one by induction, don't we? Yeah, I think we need this by induction. Yeah, here we go. Let's do some induction. But this is kind of like the base case, isn't it? Like 0 doesn't equal 1, therefore 0 does not equal the successor of any number. Oh wait, do we have this one? 0 not equal successor. We're working toward this theorem. Like I keep wanting to like use this theorem, but we don't have this yet. Right? Let's read the typewriter mode in case there's a hint. Should we be assuming this? Yeah, we need to introduce Peano's last axiom, a proof to learn about this result. Okay, yeah, so we do assume this. We are introducing Peano's last axiom. We're not 0 not equal to the successor of any number. Yeah, so this is an axiom. I keep thinking, like, I think we need this fact. And we do need that fact. Like, I was right. We do need that. Yeah, the thing is that the typewriter mode gives you all these hints that are very useful. Okay, I guess the hints are here at the bottom of the screen that I'm not reading. Okay, here we go. So now we can apply 0. This thing seems to get rid of my new lines. I don't like that. I want the new lines. Apply 0 not equal the successor of any number at h. Our goal is false, and now our hypothesis should be false as well. Is there a Vim mode in this? That would be really nice if so. I don't know. I feel like there used to be, but I haven't seen it. So, by intro H, we transform the state into goal, because our goal is this, 0 not equal 1, which is an implication. 0 equals 1 implies false. So then we introduce the hypothesis 0 equals 1 as a hypothesis, and then our goal is to show that hypothesis leads to false. This is super similar to like classical proofwriting. Then we can rewrite this hypothesis where 1 is, we rewrite 1 as a successor of 0. And then we apply this axiom that 0 doesn't equal the successor of anything. And then we should be done. This thing is buggy. Because we were done, I thought. Apply 0 not equal successor at h. Oh, and then I don't know, QED or something. Exact h. There we go. Level completed, yes. All right, so I think that this style is going to work for me in terms of transforming everything into code, into an editor. And I don't know, this probably isn't canonical. This probably is gross to like professional lean writers, but I'm learning, I'm figuring out what works for me. All right, so our theorem is 1 not equal 0, which is defined as 1 not equal 0. You know what, I don't want to call it anything. Our goal is 1 not equal 0. Okay, then we're going to intro H. Intro H. Okay, and then what that does, what is it? Double, yeah. Now we have the goal of false and the hypothesis that 1 equals 0, right? Now we're going to keep the goal false, and we're going to rewrite H as successor of 0 equals 0. And we do that by rewriting 1 equals 0. 1 equals the successor of 0 at H. Okay, seems to have liked that. I saw that at the bottom of the screen something changed, the assumptions changed. And now goal should be false, and we're going to rewrite H as false, or can I, do I flip this? What we want to do is we want to apply the 0 is not equal to a successor. I don't think that's going to work because it's reversed. We want 0 not equal to a successor, but we have successor of 0 equals 0. Successor of something equals 0. That's not the way we want to rewrite this backwards, in essence. So is there a hint as to how to do this? In the typewriter, or in the editor mode, you don't see as many hints. So here, yeah, so as it says in the hint, it's the wrong way around. And now this is what I was looking for, the sim tactic. Okay, cool. Sim tactic changes a goal and a goal that to that. So symmetric, x equals y by symmetry is the same as y equals x. Cool. Yeah, I just wish that these hints were in the editor mode as like predefined comments. That would also help me discover comment syntax, I think. So I knew that that wasn't going to work. It keeps killing my new lines, so I'm going to try to get used to it. So here we're going to, what do we do? Apply sim at H. Does that work? Ooh, that didn't do what I wanted it to. Sim? Yeah, okay. Symmetry at H. So sim is a tactic, and these things like RW, apply, and sim are tactics. Okay. So what this one does is transform this. So if I'm going to get rid of new lines, then I'm going to do it this way. So intro H transforms this line into this line. All right, so we start out with a goal of showing that 1 is not equal to 0. We rewrite our goal as a hypothesis and a implication, or taking this hypothesis, 1 equals 0, we want to show that that is false. So we rewrite the goal as a hypothesis and the goal of false. Then we rewrite the hypothesis by rewriting 1 as a successor of 0. After line 4, the state of the machine is line 5. And then we apply symmetry to rewrite H as 0 equals a successor of 0 instead of successor 0 equals 0. Now I can apply the theorem or the axiom. 0 is not equal to the successor at h. Is that right? Yeah, I think everything's still compiling. So our goal is false, and now h, we've shown that h is false, and that is our goal. And so our goal is exactly h, and we're done. Cool. Getting used to this. We're getting somewhere. Next world. What is our goal? Holy moly. 2 plus 2 not equal to 5. I think that's what we want to show. So in order to do that, we introduce a hypothesis. So that transforms our goal into false, and the hypothesis that 2 plus 2 equals 5. Right? Did I get that right? So what we can do is we can rewrite 2 equals successor of 1 at h. Did that work? 2 equals successor 1 at h. So it seems to have already expanded out everything as successor zeros everywhere. I think that there's some kind of lesson that we're missing. So let's read the hints. Didn't work. Where are the hints? No hints. Okay. Oops. This is what I'm expecting. So we rewrote 2's now as successor 1 plus successor 1 equal 5. Can I use backticks? Yeah, look at that. Okay, so we do get some syntax highlighting for backticks for code. Cool, that helps me. Let's rewrite I don't know if I'm keeping track of the state machine correctly. I think that we need a new concept in this one to show that this one is false. So what we can do is we can rewrite add successor at h. And now this is going to be successor of successor 1 plus 1 equals 5, if I understand correctly. Then we can rewrite addition is commutative at h to get 1 plus successor 1. And And then we can do another add successor. If I understand correctly. Do we have the proof that 1 plus 1 equals 2? I guess we don't really need it. We can just like slowly keep doing this. Rewrite add successor at h. Oh wait, no, not add successor. Rewrite 1 equals successor of 0 at h. And if we do that, I think it'll apply to both of these. And then we can rewrite add successor at h. To pull out a successor here. Then we can rewrite add 0 at h. Adding 0 to anything gives you the thing. I don't know if my parentheses are balanced. And now I think we have successor of successor of successor of successor of 0 equals 5. And now I'm guessing that they've added the definition of 5 to our toolbox. Otherwise, we don't know what the symbol 5 means on the right hand side, right? 5 equals successor 4. This is the first time that we've yeah, this would have been simpler. I don't know, there's probably a better way to have done this problem. There's definitely a better way to do this one, I think, but why? Your phone's messed up. The live activity is broken. Okay. All right. We can write from the left 1 equals a successor 0. Then we'll write 2 equals a successor of 1. And then 3 equals a successor of 2. And now the goal should be transformed to successor 3 equals successor 4. And now we can apply successor's injective at h. And now h should be false, goal is false, and we have exact h. Did this work? Nope. Okay, so I'm not 2 equals successor of 1. Okay, I tried to do this in my head, thinking of code this time instead of reading all the hints and seeing the intermediate state changes of the goal, goal and hypothesis. And I guess I didn't quite do it right. I mean, I feel like this is a correct proof. I think I just didn't imagine the original problem statement the way that they had it in order to prove this theorem. I'm pretty sure that my logic is correct on that. Like, it's just, let's see what the, oh, 2 plus 2 not equal 5 is boring to prove in full. I think I just did do it in full. It was kind of boring. It was super boring. Given only the tools we have currently. But I think I did it. I mean, I think we did all the boring steps. Given only tools we have currently, to make it a bit less painful, I have unfolded all of the numerals for you. Yeah, I was thinking that, I was like, I think that it's already done all the unfolding of 2's into successors and 5 into successors. Yeah, so the starting point was already unfolded with successors. So basically we just skipped all of the rewrites of definitions. All right. So let's try it again in the editor, because this is going to be real world mode, I think. Our goal is successor of 0 plus successor of 0 not equal successor blah, 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 blah. All of these. Let's get some space in here that I can read a little bit better, at least on this smaller screen. Okay, so when we have an implication like this, we want to simplify. But first I'm going to, before we do the intro, I want to rewrite this goal. So we can rewrite using add successor. And I don't think I have to say at goal or anything like that. By doing that, we're going to have successor of successor 0 plus this, I think. And we can do this again. And then we have we can pull out one of these successor zeros. And now we can, we know that adding 0 to any number doesn't change it. So we can take out this plus 0 right there. And now I have the left-hand side equal the right-hand side. What does this thing mean? No quick... Okay, so the red squiggly thing just means that we have unsolved goals. Okay, so now that I've rewritten the goal with a bunch of successors on the left, and I need to take out the ones that are talking.
Cosmetic.
Let's get rid of these out of this playlist. Remove from playlist. I don't want any of these with talking. Okay. So now, a more readable version of this would look like successor of 3 not equal successor of 4, right? This is just a more readable version of the same thing. So since this is a not equal thing, we need to introduce the hypothesis. So at this point, we take all of this. Our goal is to show that this hypothesis, that they do equal each other, is false. So to show that that hypothesis is false, we just need to apply successor is injective at H, because we have a mismatch of all of this on the inside like the inside of the two don't match, like of the outermost braces, the outermost parentheses. So I think at this point we have goal is false, H is false, and then we should be able to just exact H. But I don't think we got there. Alright, so when we applied successor injective at H, I think we unwrapped one level of successors. And that's not what I expected. I expected to be able to just do it once, but so doing it once unwrapped one version, or one of those successors. The editor, is it already rebalancing these parentheses? Is it doing that? 1, 2, 3. No. I think I just didn't have the right number typed. Yeah, I just didn't have the right number typed in this one. Okay. So each time I apply this, the fact that successor is injective then proves that the inside of the two match. So we're unwrapping levels of the successor thing. And if we apply again, apply the fact that successor is injective at H, now we have this, and then we can apply 0 is not equal to successor of any number. So if we apply that mathematical fact, now H is false, and we can say exact H. Hey, we got it. Level completed. Okay. I wonder if there's a simpler solution than that, just doing all the unwrappings one at a time. Is there a simpler? 0 not equal successor, and successor is injective. I mean, I think we essentially did do that. Did I just delete my editor mode of this one? I think I did. Yeah, I did delete that. Oh well. Hey, but I can Command Z and come back here. Great. I don't know. I feel like there may have been a simpler version of this, but basically, yeah. We pulled out adding the successor of a thing is the same as the successor of the things added. And then, yeah, so I got this left-hand side to be a long chain of successors, and the right-hand side started as a long chain of successors, and then we just kept applying the fact that successor is injective to unwrap all of those levels of successors. And we unwrapped all of those to 0 equals successor 0. And we know that 0 doesn't equal the successor of anything. So we applied that theorem here. And now our goal matches our hypothesis and QED. Let's draw a little square. A little black filled in square right there. That's... I'll come up with a better QED signature. Let's move on. Next. Oh, that was the last one, wasn't it? Hey, we completed... Look at that. We completed, what's it called? World. Inference world. Dope. So, do I get any kind of message? Like a congratulations? What? It doesn't like failed commands like putting a QED at the end? It doesn't like that? Intermediate goal solved? Okay. Even though it's a comment, it doesn't like that. Okay. Fine. The last thing I can type is exact, it looks like. Wait, what? What? What's going on now? I broke something, because it said that it was correct. I broke something. I broke something. Let's comment everything out. Let's see if we can get this thing back in a decent state. Okay, so can we, what's the best way to do this? Ah, my computer's running out of RAM. Look at that. Okay, so apply successor at H. I think I'm just hitting a bug right now. And then we apply successor at the fact that successor is injective at H again. And down here, we should just be unwrapping one at a time. The computer's running out of RAM. Yeah, so we're just unwrapping successors. Unwrapping, so we have one level on the left and 2 levels on the right. And now we have 0 levels on the left and 1 level on the right. Oops. What happened? Did I miscount? Oh, no. Yeah, so 0 does not equal the successor of anything. So we apply that. What? Oh, we apply 0 not equal successor at H. Yeah. Okay. I don't know what happened. Did I delete that? Because I thought that we definitely got the success emoji. I thought that we got the level completed emoji earlier, but maybe not. Alright, well, exact H. Did it refactor my code? Or when I hit Command Z, did it... Anyways, whatever, who cares? Alright, we completed this level. Look at that. We did it. Yeah. What are rules? Regular, relaxed, none. I haven't seen this. Game rules determine if it is allowed to skip levels and if the games runs checks to only allow unlocked tactics and theorems and proofs. Unlocked tactics are determined by two things: a set of minimal tactics needed to solve a level plus any tactics. The options are regular, relaxed, and none. Yeah. Okay, so hard mode, regular mode. I want to learn this stuff properly, the proper way. Okay, so we completed Implication World, y'all. Pause the video if you're not following along. Pause it, ask any questions. No questions in the chat right now, so take it that you all are following along perfectly and you are all becoming masters of lean alongside me. Okay, we could do Power World, Advanced Edition World, or Algorithm World. I want to do a breadth first search on this graph, so we'll start from the left and just do Power World. What are we going to prove in Power World? This world introduces exponents. If you want to define 37 raised to the end, then as always, you'll need to know what 37 to the 0 is and what 37 to d plus 1 is, given only 37 to the d. 37 to the d. You probably guess the names of the general theorems. Pow, 0, power, successor. Cool. Using only these, can you get past the final boss level? Ooh, the levels in this world were designed by Sean Carey, a UROP student at Imperial College London. Thank you, Sean Carey. Or Sion. I apologize, I don't know how to pronounce your name. Sion Carey. Funded by a fellowship in the summer of 2019. Dang! I wish I could get funded to do lean. That'd be so cool. Thanks to Sion for funding her. I apologize if I used the wrong pronoun a moment ago. Dope. Thank you. Thank you for this level. Exponentiation. Let's do this. Alright, theorem. 0 to the 0 equals 1. Ooh! That's not true. In regular math, that's not true. 0 to the 0 is undefined in regular math. But in lean, we are making a choice. We're choosing that it is 0 to the 0 equals 1. Cool. Interesting. Mathematicians sometimes debate what 0 to the 0 is. The answer, there's no debate. If you take the... if you accept calculus and you accept limits, then you can show that 0 to the 0 is 1 if you take one type of limit, and it's 0 if you take a different type of limit. So it's cool. That's interesting. It's probably because you need computers to have total functions. Like every function has a single output, not like two different outputs. Yeah, I bet that this is like an implementation detail. That's my guess. Check out the Power tab in your list of theorems to see the new proofs which are available. Cool. Alright, so we now have this new tab of powers. So power of 0. One of the two axioms defining exponentiation in this game. So, we take it as an axiom that anything raised to the 0 is 1, including 0. Neat. So if that's an axiom, then you just substitute when a is 0, then you apply pow 0, and you show that it's 1. Okay, so I want to continue getting used to editor mode everywhere as much as I can. So our goal is 0 raised to the 0 equals 1. Then we are going to can we introduce variables like what happens if I do intro age? Does that work? I want to introduce no, really, we just need to, because this already is of the form POW 0, right? Yeah, we just need to apply that axiom, as I said a moment ago when we were reading the axioms. This is just an instance of POW 0, which says that a to the 0 equals 1. And so Lean is able to see that this is an instance of that general fact. Okay, next. So in editor mode, you don't see the hints. So let's come back to typewriter mode. So our theorem is 0 POW successor. 0 to the successor of anything is 0. Alright, so 0 raised to any power is always 0. 0 raised to any positive integer is always 0. Okay. We've just seen that 0 to the 0 equals 1, but if n is a successor, then 0 to the n is 0. Okay. Alright. My computer is slowing down. If anybody wants to buy this Mac Mini M1, it is a fantastic computer overall, but for streaming and how complicated my entire environment is getting, it's a little too slow for me. Okay, so our goal is 0 to the how can I write parentheses and such? Just like, does this work? 0 raised to the successor m equals 0, right? Do we need to take the axiom of like a to the b plus 1 equals a to the b times a? I think we need that to define exponentiation. Like, we're defining... I bet that there's a new axiom that says that a raised to the successor of b equals a to the b times a. Like, we get an extra one in the multiplication. POW successor, yeah. A raised to the successor b equals a to the b times a. And we do take that as an axiom. Did typewriter mode mention that, or did it just say, check out your toolbox? I don't know. But that's exactly what I expected. And we're going to use POW successor, which is defined as this. I mean, that green against green does not look great, but sorry. So we're going to apply POW successor to our goal, if I understand correctly. Which now, or no, rewrite POW successor. My computer's frozen. Alright, so we rewrite POW successor, and now I think that our goal is going to be 0 to the m times 0 equals 0. Did that work? It didn't seem to work. Oh, wait, when we rewrite, I think we put this in a list. Yeah. I wish that you didn't have to use the list syntax to rewrite a single thing. Okay, so rewrite POW successor, and then rewrite multiplication by 0. So now, the thing that we want to prove is true is now 0 equals 0. How do we... This isn't quite... Oh wait, no, this is reflexivity, right? Yeah. Yeah, reflexivity, RFL. QED. Yeah. Yeah, you use reflexivity when the goal is of the form A equals A. Cool. Next. Let's read the nice intro. We're going to prove that for all naturals A to the 1 equals A. So 0 to the 0 equals 0, because we chose that. And then 1 to the 1 equals 1, 2 to the 1 equals 2, on and on forever. Okay, and there's no other motivational text. Let's pull up editor mode. So our goal is A to the 1 equals A. And I take it that this part here is the syntax for the lean program. Theorem something where A is a natural number, A to the 1 equals A, by, and then the by is this code, which is, I think in Haskell, this is like the do monad, and you like do a bunch of steps that are sort of stateful. So I think that this is like the stateful part of like a monadic thing. I'm talking out my ass. I don't really know Haskell that well, but like this feels familiar. This is like kind of like a stateful list of motions or something. Or statements, yeah. Alright, so goal is A to the 1 equals A. I think that we're going to do this by induction on A with H and HD. I think, so now our goal, we have two goals. One is 0 to the 1 equals 0. And goal 2 is successor of A raised to the 1 equals the successor of A. And we have we've transformed this to, for whatever reason, to H. And HD says that assuming h to the 1 equals h. But first we care about getting the base case. So this is our first intermediate goal, the base case, and we already proved this, right? Apply POW 0. Oh wait, no. Apply 0 POW? We have two different goals, H and HD. I'm so confused. Let's see the hints. Okay, so current goal, 0 to the 1 equals 0. So I want to apply 0 raised to anything. Is that not what we have? Is it POW 0? No. Yeah, POW 0 means like the first symbol is power and then the second symbol is 0. 0 POW successor. We've already proved. 0 to the successor. 0 POW 0. Oh wait, 0 POW successor. Yeah, 0 raised to any successor is 0. Okay, so, but we're not in that form yet. We need to rewrite 1 equals the successor of 0. And now our current goal is 0 raised to the successor of 0. Then we can apply 0 POW successor, right? Cool. Okay. Now we're going to do the inductive hypothesis. Why did it use A? Wasn't expecting A. Assumptions HD, H to the 1 equals H. Yeah. Okay. Yeah. Alright, so now we're ready for the inductive step. So we want to show that the successor of A raised to the 1 equals successor of A, given the hypothesis that A to the 1 equals A. So assuming that A to the 1 equals A, then we want to show A plus 1 raised to the 1 equals A plus 1. And so the right track here? Yeah, okay. I think I see it. Alright, so we can rewrite 1 equals successor of 0 at HD. And then we can apply, or do we rewrite? I think we rewrite power raised to the successor at HD. Is that the right naming? So I expect that this is going to be successor A raised to the 0 times successor A. And then I think that we're going to rewrite anything raised to the power 0, or anything power 0 equals 1. And then we are going to multiplication by 1 at HD. Do we have this one? I think it compiled. Multiplication by 1 is always equal to the thing, and now this is reflexive. The left-hand side equals the right-hand side. Did that not work? Do I say reflexivity at HD? Okay, so we got, oh, wait. We're at H equals H. Where are we? This didn't work out the way I thought it did. All right, 1 times H equals H. Oh, I've been rewriting the assumption everywhere. Oh, no, okay. I've been doing this wrong. I've been meaning to rewrite the goal. Yeah, I screwed this up. Oops. Still getting used to this stuff. All right. Okay, but I've been, so I wrote these things in wrong. Let's just do this whole proof again. Okay, at this point of the state machine, we have completed the base case. And now So we've completed the base case and we have the inductive hypothesis h to the 1 equals h. Now we want successor of h raised to the 1 equals successor of h. And so we need to be transforming the goal, not transforming the hypothesis. So this is not the HD. HD, yeah, H, I don't like this naming. Like, I just don't like the choices of variable names. And I think that this is arbitrary and it could be different. But HD is the inductive hypothesis. So assuming that a to the 1 equals a, then we want to show successor of a raised to the 1 equals successor of a. And so now it's going to be the same kinds of steps that we were doing, but I shouldn't be applying them to H or HD. I should be applying them to the goal. So we don't say rewrite something at HD. Everywhere where I was typing HD, I meant to be typing the other thing. I'm surprised we didn't get like compile failures and whatnot. But we're going to rewrite 1 equals the successor of 0. And now the goal is going to be rewritten this way. And then we're going to apply, excuse me, the definition of raising to the successor of a number. My computer's so frozen. So annoying. All right. Apply apply power successor. That didn't work. Pow suck a raised to suck b equals a to the b times a. That's what I'm expecting. Do we rewrite? Yeah, oh, that makes sense that it would be a rewrite, wouldn't it? Not an application. Application is more for implications. You apply implication theorems, I think. So now we rewrote this goal now as suck a to 0 times suck a. Okay. And now we're going to rewrite, or no, wait. I don't even know. We apply or rewrite POW 0. This is more of that's like an existential statement that anything raised to the 0 equals 1. What I want is to rewrite suck a raised to the 0 equals 1. Which one is it? Did I do it right? Yeah, okay. So it was rewrite POW 0. So we had something power 0, so we could rewrite that as 1. Okay, we're getting somewhere. Now rewrite is this a thing? 1 multiplication by 1? Yeah, okay, that worked. 1 mul. So 1 times anything equals itself. And then at this point, our goal is suck a equals suck a. And then we're going to apply, if I can remember correctly, apply the fact that successor function is injective. So I believe that now our goal is A equals A. So I don't know where we ever used the inductive hypothesis. I don't think we needed to prove this by induction. Yeah, we didn't need to prove this by induction at all, did we? Or... I don't know. Apply successor is injective, and then refle it. Refle. At this point, successor is injective. I broke the REPL. Unknown identifier suck inj. Is that not the naming? Suck inj. Do we... Oh my gosh. Do we rewrite suck inj? Is that it? No? I thought we apply suck inj. Well, it doesn't matter. We have left-hand side equals right-hand side on this in this goal, so I think we can just refle it, and then our level is complete. So I don't think I ever used the inductive hypothesis, so I think that we can... I think we could rewrite all of this as just a more straightforward proof. So let's try this one again without induction, because we never used the inductive hypothesis. A to the 1 equals A. Rewrite 1 equals successor 0. And now our goal should be, oh my gosh. I just want to learn how to do this exact same game in my command line instead. And now we can rewrite pow suck. And this is going to be A to the 0 times A. And then we're going to rewrite pow 0. Anything raised to the 0 is defined as 1. And now we rewrite 1 multiplication. And now the goal is A equals A, so we get a refle. QED. Look at that. Okay, so we didn't need an induction here. Cool. Okay, I think that the timer went off a while ago, so I'm gonna take a short break. Let's take a longer break this time. We've been going for a while. Hey Siri, set a timer for 10 minutes. All right, we're making progress. Feeling very good. I kind of want to maybe call it a day after this. I want to get through this entire world. We can finish this world in the next Pomodoro. Let's go to the next level. Theorem 1 pow. 1 raised to anything equals 1 for every natural number m, including 0. Yeah. Okay. Yeah, this one seems pretty true. We can do it. Okay. I'm gonna, if there's no questions or comments to respond to right now, I'm gonna go get a coffee. I'm gonna go get another coffee. Okay, be right back. Okay, I'm back. What's going on? What's up, y'all? Let's see if we can clear out some RAM usage or something so that the music doesn't die out as often. Are you all having fun? I am. I'm having a lot of fun here. This is so cool that nowadays you can actually write mathematics and do proof-based mathematics in a code editor. And like you can actually run it through a computer program and get proofs. So this week is number theory. This week is also proof strategies. And what we're doing right now is like the most modern form of proof strategies. What we're doing is lean, and this is computer-assisted proofs. I think it's freaking cool. I hope you think it's freaking cool too, because it is freaking cool. It's a little cold over here. Ugh. We're gonna do one more Pomodoro, and then I'm gonna practice the classical guitar. I'm actually gonna practice because I have my lesson at 2 later today. I have my lesson in like 2 hours. So we're getting somewhere. We're making real significant progress. I feel major progress especially because I'm finding a way that I can use the editor mode, which feels a lot more familiar and easier for me to think in, as opposed to the typewriter mode, which is much more kind of like tutorial-y. What I would love to do is figure out how to get my local environment set up so I can code these in the terminal instead of in the web browser and do the exact same natural number game in the terminal. And it completely makes sense to me that they haven't prioritized that. Makes sense. No, I'm not complaining in any way. This is amazing that they've set up this lean environment in the browser so I don't have to deal with all the installation steps and everything, which is always a pain in the ass whenever you're learning to code anything new. It's super cool that there's an online environment for this. All right. This stuff is so much like test-driven development in coding, in normal day-to-day software. It's so much like unit testing that I think it's phenomenally cool. It's like unit testing for mathematics. Test-driven mathematics. 1 power for all naturals m. 1 raised to the m equals 1. Huh. We can do it. I believe in ourselves. This is so dope. We're literally going through all of the piano axioms and building arithmetic from the piano axioms in a proof-based way. It's the same exact proofs and theorem statements that you do when you do it on paper. It's just that we're writing it in code. It's pretty cool. Pretty freaking cool, if you ask me. Alright, break is about over, so here's our goal. 1 to the m equals 1. And everywhere, in some way, we've scoped, in this entire theorem, we say m is a natural number. M is of the type natural number. And then, this is cool that it looks like we had to specify the type of 1, because 1 can be ambiguous. 1 is a real number. 1 is also a complex number. 1 can also be the element of, the ring of integers mod p or something. I don't know. So we specify 1, like the normal counting version of 1, not a more complex 1. So the theorem is of this type, and it's defined as colon equal by a list of steps. And I think that in this we're escaping into some kind of do monad. Hey Siri, set a timer for 30 minutes. Hey Siri, set a timer for 30 minutes. Okay, let's do this. Let's keep going. So our goal is 1 to the m equals 1.
It's canceled. For how long?
30 minutes.
30 minutes starting now.
On this one, do we need induction? Or can we just start by rewriting ones as zeros and successors? I think that we can do that approach. But first, can I clear out some activities, some programs? What? It's always Figma, and that makes sense. I forgot to quit Figma. Like anytime I make a thumbnail for one of these streams, Figma takes over my entire RAM. That makes sense. Discord is running, isn't it? I can close out Discord. Google Drive is taking a tiny bit. Safari graphics and media. Ooh, I got a bunch of notifications. YouTube is taking up a gig of RAM. I wish I could just prioritize. Can I just prioritize the natural number game? I mean, this site is taking up like a gig and a half of my RAM right now, which feels like a lot. All right. Anyways, hopefully we'll be more buttery smooth by clearing out Figma and Discord. So let's rewrite 1 as the successor of 0. And I think that's going to transform that in both places. If I understand correctly. And now... equals successor 0. I don't think so. I think that this is easier to do by induction. Do they give us a hint to do it by induction? No hints? No hints on this one? Alright. We're losing the hints. We're losing the friendly language. Alright. Our goal is 1 to the m equals 1. We're going to do it by induction on m with... can I change this? Can I reuse the variable name m? Because as I understand it, the first one is the variable name, and then the second one is the inductive hypothesis. Does this work? 1 raises... Yeah, I think so. Yeah, so we've got the base case, the base goal, and then the future goal. 1 raised to the suck m equals 1. Yeah, because I don't like changing the variable name in an inductive proof just to remind everybody that we're doing an induction proof. Alright, so now our goal should be 0 raised to the... Oh wait, no, 1 raised to the 0. It's like our first goal of 2 is that 1 raised to the 0 equals 1. And I think, yeah, we have, I think we have that theorem, POW 0. And now goal 1 of 2 is anything raised to the 0 is 1. So we have 1 equals 1, and now we have reflexivity. Now we move on to goal 2 of 2, which is now 1 raised to the successor of m frozen editor. 1 raised to the successor of m equals 1. Given the inductive hypothesis that 1 raised to the m equals 1. So what we can do is we can rewrite. Where are we? Come on, code editor. Rewrite power raised to a successor. Any power raised to a successor is 1 to the wrapped number times the base 1 extra time. And then now we can rewrite multiplication by 1. And now we can apply the inductive hypothesis. So the goal is exactly the same as h. Wait. This didn't work. Okay. Didn't work the way I thought it would. We've got a red squiggly line on POW 0. So did it not apply? Yeah, it didn't find the, Oh wait, why did I say POW 0? What we meant here was POW successor. There we go. Alright, so POW successor, we rewrite 1 raised to the successor m is 1 to the m times 1. And then we apply multiplication by 1, and then we show, well, our goal is exactly the same as the inductive hypothesis. So we're done. Level completed. Look at that. Next. Theorem. POW 2. For all natural numbers a squared equals a times a. Let's see if we can do this without reading any hints. So, goal is a squared equals a times a. Wait for my computer to catch up. What can we do? We could just stop the music at this point. Let's just stop the music. I'll get buttery smooth. Streaming. Y'all have heard the music already at this point. Can I clear out? Can I kill the process that's taking up all my RAM? VT encoder XPC service. I'm guessing, I mean, that's the biggest offender, and I think that that is coming from OBS and streaming. There's a bunch of cached Safari content. Anyway, whatever. Hopefully this will be a little smoother now. All right, so let's rewrite. 2 is the successor of 1. Still lagging, still freezing. Okay, you know what I want to do? I want to write the steps in like a human readable, like what is the math that I want to show? Like if I were writing this on paper, like a traditional classical proof, what are the steps that I'm doing? Like a little closer to that. So the steps that I want to do is that 2 is the same as the successor of 1, and then raising anything to a successor is raising it to the wrapped number and then multiplying one more time, a to the 1 times a. And then I want to say that raising anything to the 1 power in lean, it is always true that raising anything to the 1 is the same as the base number. So the left-hand side is going to be rewriting a raised to the 1 as just a. Now the left-hand side is a times a, and the right-hand side is a times a, and so our proof is complete, QED. Okay, so this is just rewrites. So now's a good chance for me to try this. Can I rewrite, this looks like a list. So I think that I can list all the rewrites, and it looks like I can even line break it, which is cool. So the first rewrite is the 2 equals the successor of 1. And then I'm going to rewrite a power raised to a successor for the second, to go from the second line to the third. And then from the third line to the fourth, I'm going to say power raised to the 1. And then we're done. Yeah, cool, look at that. It's getting sexier and sexier. We can, I can write out the math, write out the steps, and then write the lean proof here. Cool. That's nicer. Was there any cool exposition? Note, this lemma will be useful for the final boss. Can't wait to get to the final boss. The final boss. It is nice that in editor mode, if you don't want to be thinking in video game terms, that you can just focus a little bit more on the code. I wish that were a configurable option. Because at some point, to me, it starts to feel distracting. Personally. Theorem. A raised to the m plus n equals a to the m times a to the n. Do we need induction for this? Maybe. Goal. A raised to the m plus n equals a to the m times a to the n. We could do it by induction on A. But I don't think that works well, because then in the inductive step you have a plus 1 raised to something, and we don't have great facts about what a plus 1 would be. We could do it by induction on maybe m or n or something. I think that's the way. I think we're going to do induction, I want to say on the rightmost variable, induction on n with, I want to just keep the same letter name, n, and the hypothesis, the inductive hypothesis, h. So now we have, we're going to do goal 1 is going to be a raised to the m plus 0 equals a to the m times a to the 0. So you prove by induction by first doing the base case n equals 0. We complete that proof, and then the second goal, part 2 of an induction proof, is going to be a raised to the m plus successor of n equals a to the m times a raised to the successor of n. Just put those parentheses everywhere. And we're going to then prove that. Okay, so for goal 1, so the left-hand side, m plus successor n is the same as a raised to the successor of m plus n. Which is equivalent to a raised to the m plus n times a on the left. And I'm just going to use a ... to mean like ditto or something on the right hand side. And then a raised to the m plus n times a is, well, now we can use the inductive hypothesis that this is a to the m times a to the n. And now we have times a equals ... And now we can do a commutativity or an associativity, remembering that lean is, if you don't write the parentheses, that it binds the parentheses to the left two variables. So then we're going to get successor of n. And then this is exactly the same as the right-hand side. So these are the steps. Okay. So why don't we put the lines of code near each of the individual goals. This is like goal 0. So now for goal 1, we're going to rewrite plus 0 to go from line 6 to line 7. This is a series of rewrites, isn't it? I think it is just a series of rewrites. So plus, oh no, not plus, add 0. So we add 0 from line 6 to line 7, and then from line 7 to line 8, on the right-hand side, we're using power to the 0 to rewrite a to the 0 equals 1. And then we rewrite with multiplication by 1 to go from line 8 to line 9. And then we have reflexivity. A to the m equals a to the m. Then, now for goal 2, we have this inductive hypothesis. So we assume that the statement is true for the number n, and then we want to show that it's true for the successor of n. If I'm going to omit the thing on the right, let's omit it on the left, the parentheses. Okay. So we should be at the second goal now. A raised to that stuff. And then what we do is a series of rewrites. First, adding a successor is the same as successor of stuff. You can like pull out the successor to the front of the addition terms. So that's like from line 18 to 19. And then from line 19 to 20, we're applying the power rule, power to the successor. And then we are now using the inductive hypothesis. So how do we do this again? Apply H. Is it apply H? That's what I would guess. I don't think that worked. Did it work? Tactic apply, failed to unify, a raised to the m. Do we rewrite H? Because I do see that here's H. do I do H in brackets? No. I don't think I rewrite H, do I? Do we rewrite H? Oh, yeah, okay, that worked. Okay, so we rewrote the hypothesis into the goal. So the right-hand side, we had the left-hand side, and then we substituted in the right-hand side of the hypothesis. Okay. So now we're at line 21. Then to go from 21 to 22, what was the step? What's the step called? Yeah, I think that we need to rewrite multiplication as associative. Mul-assoc. Yeah, and now we have the parentheses on the right of that multiplication, as I expected. And then we, can I do this? Left arrow, power to the successor. Can I include the left arrow in a list? Yeah, that worked. Great. A to the m times a to the suc n. So now the left-hand side equals the right-hand side, and we just have to draw a little nice box and say QED. Riffle. We should be done. Level completed. Great. Cool. Okay, that was fun. I don't think that there was any neat exposition. Let's now begin our approach to the final boss by proving some more subtle facts about powers. I wonder if there's exposition in the middle, like as you do the intermediate steps. I'm pretty curious if there is exposition as you solve this thing, but I think we got it. Next. Multiplication to a power. So a times b raised to a power n equals a to the n times b to the n. Okay, we can do this. So our goal is a times b raised to the n equals a to the n times b to the n. I think that we have to do this by induction. Let's write out the human readable version of this proof first. And let's try something a little fancier. Yeah, I broke everything. I broke it. Let's use the multi-line comment this time. Error fetching goals. RPC error undefined. Pending response rejected since connection got disposed. I'm sorry, I broke it. Try again. I haven't done anything yet. Typewriter mode. Crashed. Go to editor mode and fix your proof. I tried. Client is not running. Try again. Can I refresh the browser? I think that this should be fine. Yeah, okay. So just refreshing fixed it. Okay, so I think that this is going to be by induction on n. And I want to give this a slightly nicer name. We're so close. We're at part 7. My lesson is at 2. Let's do one more Pomodoro. Hey Siri, set a timer for 30 minutes.
30 minutes starting now.
I can cram before my lesson. So I don't like using super terse names for something like an inductive hypothesis. I want to use terse variable names for the variables, but not something like a hypothesis. It just like hurts the readability, if you ask me. And I'm going to even call this a sub-goal, because, or goal 1 of 2. I don't know. Sub-goal 1. We need to show in the inductive method, we show a times b raised to the 0 equals a to the 0 times b to the 0. We're going to show that. And then we're going to show this, the secondary sub-goal, that a times b raised to the successor of n equals a to the successor of n times b raised to the successor of n. Using the inductive hypothesis that a times b, so if we assume that a times b raised to the n equals a to the n times b to the n, then we want to show that the same statement is true for the successor of n, assuming the inductive hypothesis. Okay, so for the base case, well, we just do a few rewrites and say, so I'm curious if we need to do 3 separate statements for lean, or if I just say, if I just rewrite POW 0, is that going to apply to all 3 POW 0s in this statement? I don't think so. I think I have to say POW 0 3 times. But I could be wrong. So POW 0 is defined as 1, and then we'll have 1 equals, if I understand correctly, it's 1 equals a to the 0 times b to the 0. And then we have 1 equals 1 times b to the 0. And then 1 equals 1 times 1. And then 1 equals 1. And then we get a REFL. For the second proof, why don't we... let's use it the other way. Inductive hypothesis is this, and then the sub-goal 2 is this. And then, so assuming the inductive hypothesis, then we're trying to prove this sub-goal 2. For this inductive hypothesis, or sub-goal 2 a times b raised to suck n equals dot 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 blah blah blah. We're going to do a times b raised to the n times a times b. Why did the color change here? Oh, because doing two multiplications in the code editor is it's treating that as like a bold or something like that. Oh well. A to the n, a times b raised to the n times stuff. I'm just going to work on the left-hand side. At this point, we can apply the inductive hypothesis. A times b raised to the n splits as a to the n times b to the n. A to the n times b to the n times a times b. Now we can do associativity of multiplication. And if I understand correctly, we'll still keep that grouping. And then we can do I think I might be repeating a proof, but I think that there's a theorem in between, like associativity, commutativity, but whatever. Left associativity in that thing. B to the suck n. Commutativity. Associativity. Definition of power to the successor in reverse. A to the suck n times b to the suck n. And now we have left-hand side equals right-hand side. Yep. Cool. So there's the proof. Let's translate all that into lean. I still wrote out every single step in between, fully with all the details. So we just need to translate each of these steps into lean statements, and they're all rewrites, I believe. So here was my first question. Power to the 0. Does that apply to all of them or just to the first? It only applies to the first one. That's what I thought. And in like the syntax tree, it is going to apply to the first pattern that matches that. It doesn't apply to every power or to every pattern that matches that. I know that there's something called repeat, and you can repeat and just keep applying the same tactic again and again. But yeah, multiplication by 1. And now we have reflexivity. So then we move on to this sub-goal. I already sketched out exactly the proof that I expect. using this inductive hypothesis, so we use the definition of power raised to the successor. And we should see that transform like that. A times B raised to the n times A times B. And now we're going to do multiplication is associative. That's going to rebalance the, no, is that what we want? Oh, no. What I did here was I applied the inductive hypothesis. Yeah. So inductive hypothesis to substitute there, and now we can do multiplication is associative. Now we can do what I would like to do is multiplication is commutative within that one bracket. I think, yeah, that's what I did in my sketch up here. It's a little hard because I think we need to do the third instance of multiplication. But can we use the other form? Like, multiplication is commutative on A times B. Does this syntax work? I didn't think that was going to work. A times B, I doubt I need the space, right? Yeah, I didn't think that was going to work. All right, so now, can I leave a trailing comma? I want to learn how to use this precision rewriting. Oh, it's frozen. It keeps freezing. Multiplication is commutative using A times B. Come on. This didn't work. How do I target that one? Do I need parentheses? If I include parentheses, does that fix it? Did I already try that? If I take out the spaces, does it work? If I take out the parentheses and the spaces, does it work? No. Okay, so at this point, are there any hints in the typewriter mode? Does typewriter mode give you hints along the way? Nope, I don't think so. So we're going to do the nth rewrite of multiplication is commutative. Oh wait, no. Nth rewrite, and I counted that it was the third multiplication in the syntax tree of multiplication being commutative. In the syntax tree on the left, we have 1 on the outermost, this thing times this thing, and then another one inside that, and then another multiplication inside that. So it's the third multiplication that we want to rewrite. Are we still wrong? Is that still wrong? What's wrong? Oh, no, that worked. Okay, so we got it. B times A right there, as I wanted. Okay, and now that we have that, there's our proof of that step, and we can continue rewriting. So I did my B times A. Now let's redistribute the associativity. Multiplication is associative. Oh gosh, okay. And if I do that, how is it going to... I want to get associativity of the second multiplication. And we need to write it from the opposite direction, in a sense. Yeah, okay. And so we need nth rewrite, and the second multiplication all right. Yeah, so I got the implicit parentheses around b to the n times b. And now what I wanted to do next is I wanted to rewrite the reverse version of power successor of the power successor rule. So now we have b raised to the successor n, as I wrote in the comment. And now we can then rewrite within that within the parentheses, which means the second nth rewrite. The second multiplication is commutative. And now we can rewrite the reverse version of the rule of multiplication being associative. And now here's the implicit parentheses a to the n times a. And now we can rewrite the reverse version of the power to a successor. So now we have a to the successor n times b to the successor n equals a to the successor n times b to the successor n. This is exactly the same steps that I wrote out in the comment sketch. So let's just clean up this proof. Let's just clean up this proof a tiny bit. This is so fun. This is great. I love this. I love this a lot. All right. Now we should be done. If I rerun the program by typing another character again, we should get the... Oh, I don't think I typed my refl. Haha, level completed. We got it. We just proved that for all natural numbers, a, b, and n, a times b raised to the n equals a to the n times b to the n. This is dope. This is such a cool thing. This is very niche. This channel is very, very niche, but I promise you we're learning some cool things here. And it really, truly is number theory, too. Natural numbers, y'all. All right, next we're going to prove this property. If you raise a power to another power, it's the same as multiplying those powers. I don't have time to do it right now on stream. I think I'll finish this on my own, and then tomorrow I'll just quickly skim through all of this world. And tomorrow we will return and So I'm going to finish Power World on my own, and then tomorrow we're going to take a look at Advanced Addition World, and soon we'll get to Algorithm World, and then Inequality World, and then Advanced Multiplication World. This is so cool. This is such a cool tutorial. I love it. Thank you, everybody, for watching. Thank you to Adam for creating this website, and for everybody who worked on the natural number game. This is such a freaking cool thing. I'm very excited to learn all this. Thanks for watching. I'm going to go.